Okay, geometry fans, our topic for today, this is the first section in Chapter 8. It is called the Geometric Mean. And before we start, let me give you your joke of the day. Why did the Scarecrow win an award? And the answer is because he was outstanding in his field. Okay, so we're actually taking the notes on your own paper today. And we're going to kind of show what a geometric mean is. And then I'll show you how you can use it in geometry with right triangles. So if I gave you a pattern here, 1, 4, 7, 10, 13, ... you would look at that and you would say that, okay, the pattern is that each time you're adding 3. So to get from 1 to 4, you add 3. To get from 4 to 7, add 3. 7 to 10, add 3, and so on. This is called an arithmetic sequence. An arithmetic sequence. It means you're adding a common value. And it could be subtraction. You could go minus, minus to create a different pattern. Now, you've seen the word mean before, probably in Algebra 1 or back in middle school. And mean is an average. An arithmetic mean, so arithmetic, I'm just going to use quotation marks, that's the same thing. Arithmetic mean is another word for average. If I take two numbers, if I take 1 and 7, and I take their average, 1 plus 7 divided by 2, what we'll get is the number in between. If I take 7 plus 13 and divide by 2, we get 20 divided by 2. We get the number in the middle, that is 10. So with arithmetic, you're adding your numbers and dividing. Now, if I take a different set of numbers, 1, 3, 9, 27, 81, ... Now this time, this is not arithmetic because we're not adding each time. You can look at that and say the pattern is we are multiplying. This time we're multiplying by 3 every single time. This is what we call a geometric sequence. Arithmetic, you're talking about addition. Geometric, you're talking about multiplication. Now there is such a thing as a geometric mean. Now we'll define it here in a second, but now if I look at my numbers, let's say I take 1 and 9. If I take 1 times 9, I get 9, and then the square root of 9 is 3, which is the number between. If I take 3 times 27, I get 81. The square root of 81 is 9. The number between 3 and 27 is 9. Here's the definition of a geometric mean. It's a number, we'll call it x, between two other numbers. I'll say two numbers, and I'm going to call those A and B, where A over x equals x over b. This kind of comparison, with arithmetic you're adding, but with geometric you're dealing with multiplication, so this is a proportion. Okay, so for example, what is the geometric mean? So we'll say find the geometric mean. Find the geometric mean. Here's example number 1. Find the geometric mean of part A, 4 and 16. Okay, so what we're looking for is a number between 4 and 16 where you would have to multiply the same time to get to that number and then to get to 16. Now what we'll do is we'll say 4 over x equals x over 16. Okay, x is the number between. And to solve this, we cross multiply. X times x is x squared. 4 times 16 is 64. And then to solve this, we take the square root of both sides, and we get x is equal to 8. Okay? And when we take a geometric mean, we're looking for the positive value between those. So if I solve this, technically negative 8 is also a solution, but negative 8 is not between 4 and 16. 8 is the geometric mean of 4 and 16. And if I put the 8 there, you would go times 2 and times 2. Okay, part B. How about 5 and 20? So what's the number between 5 and 20 where 5 over that number equals that number over 20? So it's a proportion where these two numbers repeat. They're the same. Okay, let's cross multiply and we'll get x times x squared equals 5 times 20 is 100. Take the square root of both sides, x is 10. Now, it doesn't always have to be a perfect square. You don't always have to get a perfect square to do this. So example C, let's say we did 3 and 200. So 3 over x equals x over 200. One thing you might notice, there's some shortcuts here. X and x are always going to multiply. These two numbers are always going to multiply. So 5 times 20 was 100, and then what did we do at the end? We always took the square root. 4 times 16 is 64, and then we always took the square root. So one thing you can do to kind of save yourself a little time is you can just say, okay, 3 times 200 is 600. Now that's x squared, so then I have to take the square root for that. Now, the square root of 600, I'm going to think of that. A perfect square that goes into 600 is 100. I'm going to write that as 100 times 6. That's still 600. Now, 100 is a perfect square. I'm going to take the square root of that, which is 10, so I can pull that out. And the answer is 10 square root 6. That is the geometric mean. So it's not always going to be a nice integer value. It can be a radical solution to that. So that's called geometric mean. Now, you might be thinking, well, this seems a little bit more like algebra, and where's the geometry in this? So how are we going to use this? Well, in part 2 here, we're going to look at the geometric mean in right triangles. Something very interesting is going to happen when you look at right triangles. There's going to be a special situation that comes up that we can take a look at. And it's going to start, we're going to draw a picture here. If we have a right triangle, and I'm going to name this A, B, and C. And if, actually I'm going to put the C here. You'll see why later. Sorry about that. A, B, C. So here's my B. And if we label the sides of that, opposite angle A, we'll call that little a. Opposite angle B, we'll call that little b. And then opposite angle C, we will call this little c. Now, if we take this right triangle, and let's go ahead and drop an altitude here. In altitude, I'm going to name that ALT. An altitude of a triangle, by definition, an altitude of a triangle is a segment from a vertex to a side and is perpendicular to the side, perpendicular to the side. And perpendicular again means 90 degrees. Okay, so we know if I draw this altitude, what I've created is a right angle here. Now the point, I'm going to call this point D. And what that does is it actually takes the big right triangle and it makes two small ones. Because if this angle's 90, angle ADC also has to be 90. So what we have is 1, 2 small right triangles, and then the big one is also a right triangle. Now some interesting things are going to happen here. If we take the big triangle, okay, so I'm going to redraw that. So there's A, B, C. And I'm going to label the original picture here again. We have the altitude. In the big triangle, the long side is called the hypotenuse. And the two sides that make the right angle are called legs. So in the big picture, here's a leg, and here's a hypotenuse. Right there. Leg, hypotenuse. Now the legs are different. They're not the same. So we've got leg, here's the hypotenuse. And if we take the big triangle, let's compare it to one of the small ones. Let's compare it to triangle ACD. Now remember, that's a right angle. Notice that they both also have angle A. Now, if I look at, here's the big triangle, here's my angle A. I'm going to label that with one arc. In the small triangle, it's the same angle A. So both of those will be one arc. Those are going to be congruent. Now the angle C's are not congruent because in the big triangle, angle C is all of this, that's the 90, but in the small triangle, in the small one, then that angle is not the same as the 90. Okay, so these are not congruent. But notice that what happens here, we have two pairs of congruent angles. And what that tells us is because of that, we can say the two triangles have to be similar to each other. Okay, so what happens is we can say that triangle ABC is similar to triangle. Now A matches to A. B has no marks. That matches to C with no marks. And then angle C, the right angle, matches to angle D, the right angle. So what we've got here is triangle ABC is similar to triangle ACD. Okay, so we know that those two are similar. Now, at the same time, let's go ahead and compare that to the other small triangle. So over here, I'm going to draw triangle CDB, which is another right angle. So there's C, D, and B. Angle D is again the right angle. Now, in this case, notice that these two triangles both have angle B. Okay, so down here, I'm going to label angle B with two arcs, and this will be with two arcs. So again, what's going to happen is these are similar by angle. So the reason the similarity postulate is angle similarity. If two pairs of corresponding angles are congruent, then the triangles are similar. They have the same shape, but the sizes are proportional. Okay, now if I'm comparing the big one and this small one, triangle ABC, okay, so I'll actually use this again. Triangle ABC is going to match, A is one arc. Now the one arc here must be angle C, so that'd be triangle C. B has two arcs, that matches to itself, and then the right angle C matches to the right angle D. And because this triangle is similar to both of the small ones, then the two small ones also have to be similar. Okay, so what happens here is that when you have a big right triangle and you draw an altitude from that right angle, when you draw that altitude, it creates three similar triangles. Now that's the end of part one, and we haven't gotten to the relationships yet, but in part two, we're going to talk about that.